I developed a classification of these many types of damage into a manageable number of categories, just 7 categories.
What's different from the 12 hallmarks of aging then?
A lot of people said that this whole approach was not scientific. They didn't really understand anything I was saying. But after about 10 years of repeating myself and explaining myself and so on, I pretty much won the argument. So that paper has become by far the most highly cited paper in the whole of the biology of aging this century.
Okay, I understand we're trying not to make people old, but what is the end goal? Make everybody live forever?
So everyone says that. But really, no. The end goal is simply to make everyone stay healthy forever.
I'm Dr. Esra Çavuşoğlu, and I've been living a sober life for the past 19 years. My battle with addiction drove me to seek new methods, devices, and supplements to improve my physical and mental performance, enhance my quality of life, and ultimately live healthier for longer. From my experiences in addiction recovery, biohacking, and longevity to the latest global developments, from groundbreaking entrepreneurs to expert academics, the conversations I've had over the years are now featured weekly on Soberhead Podcast. Today on Soberhead Podcast, we dive into one of the biggest questions in science. Can aging actually be solved as a medical problem? My guest, Dr. Aubrey de Grey, often called the godfather of the longevity movement, believes aging isn't a disease. It's a maintenance issue, much like keeping a classic car running smoothly. In this episode, we explore his 7 categories of aging damage, the promise of stem cell therapy and gene therapy, and why preventative maintenance may be the key to extending not just lifespan but health span. We'll talk about senescent cells, rapamycin, and what current research in mice is revealing about how multiple interventions, not just one, may hold the real breakthrough. Dr. de Grey also opens up the challenges of funding, the limits of hype, and what it will take to turn science fiction into science fact. His forecast is that there's a 50% chance we will reach longevity escape velocity within the next 12 to 15 years. Get ready. This conversation will change how you see aging, health, and your own biology. This episode of Soberhead Podcast is brought to you with the support of Gedik Foundation for Education. For over 30 years, Gedik Foundation has been providing opportunities for youngsters, children, and women to realize their dreams through scholarships, projects, and social work. And we're proud to be on this journey together. Investing in education is investment in the future. Subscribe and support us in our quest to bring you the most current scientific data and continue your access to the world-renowned experts in their fields as guests on Soberhead, with Turkish translation and completely free of charge. Comment on the episodes, like, and share. Dr. Aubrey de Grey, welcome to Soberhead Podcast. This is a very exciting moment. The reason is anybody and everybody in the world today is talking about longevity, like people who knows about longevity, people who are doing just aesthetic procedures, people who are even coloring hair are talking about longevity. And I'm like, finally, I have someone, I had many important, amazing guests, but you're often called the godfather of the longevity movement. You're famous for this revolutionary view that aging, in fact, is a disease, and I'm going to ask about that in a couple of minutes. You spent your career arguing that we can defeat it by repairing the cellular damage, and you kind of giving referring it like to a car, actually. And in a couple of your talks, I saw these very beautiful antique car that you were referring to. You've been facing for so many decades this pushback, this skepticism, and people who were downplaying what you were trying to defend. And finally, for a decade now probably, but you successfully pushed the idea from the fringes to right into the mainstream. So it's a pleasure to have you here. Welcome. So, there's so many things to say about you, but these are, I think, the most important points to describe who you are to my audience if they never heard someone called Aubrey de Grey, but it's quite impossible, but still. So welcome.
Well, thank you for having me on the show.
Because you're the best person who can explain that. What do you exactly mean by aging is a disease?
Well, actually, I want to start by giving a small correction to what you said about aging being a disease. because I do not actually call aging a disease. I call it a medical problem, but that's not the same thing. So I want to explain the difference. A disease, like an infection, is something that, mentally we have an image that it's something we can cure with medicine. Most infections, of course, we can already cure. Some of them we can't cure yet, but we're working on it. But we should not think about, for example, Alzheimer's disease in that way, because Alzheimer's disease is a consequence of having been alive a long time. It is intrinsic, non-communicable, as some medics say. And therefore, the idea of curing it just kind of doesn't really make sense in the same way. We can, however, very much address it with medicine, postpone it, maybe postpone it indefinitely. And that's the same for all of the age-related so-called diseases. Almost all cancers, heart disease, these are things that we cannot cure, but we can postpone them, perhaps indefinitely, with medicine. And the reason it's so important to say all this is because the exact same thing applies to things that are aspects of aging, but we do not call diseases. When we see that someone is losing their cognitive function or is losing their physical function, we may say that they have this or that disease, but we may just say it's frailty or something poorly defined like that. And we don't call that a disease, typically. But that's a problem, because when you call something like Alzheimer's a disease, and you don't call frailty a disease, then you give the impression that things like frailty are inherently off-limits to medicine, that there is no way we can postpone them or address them with medicine at all, even in theory. And that's complete nonsense. So the key thing I want to highlight is that there is no meaningful difference between the aspects of aging that we give disease-like names to, such as Alzheimer's, and the ones that we don't, such as frailty. The difference is purely semantic. All of that can, in theory, be addressed with medicine, and that's what we're working on.
So what is aging then?
Well, so I like to define aging as the combination of two processes. A process that goes on throughout life, literally even starting before we're born, which is the creation of damage in the body, molecular and cellular damage, as a consequence of the body's normal metabolism. In other words, the network of processes that the body performs all the time in order to keep us alive from one day to the next. That's the first process. And the second process starts late in life, and it is the decline in function, both mental function and physical function, that is caused by having too much of this damage. What is too much? Well, the body is built to tolerate a certain amount of damage, but only a certain amount. So that's why until the damage has accumulated to that amount, which takes most of our life, then, physical and mental function remain more or less intact. And it's only later on that they go downhill. So the reason why I like that definition of aging, that it's a combination of these two processes, is that it helps us to crystallize and to think about how we might develop medicine to address it. Addressing aging in those terms means that we want to separate our metabolism, the normal operation of the human body, from the pathologies of late life. There are various ways that we might do that. We might develop geriatric medicine, which makes the mistake I was talking about earlier and tries to essentially cure the pathologies of late life. It doesn't work. We spend a huge amount of money trying to make it work, but it doesn't. And it's obvious why it doesn't work, because this damage that I'm talking about, these molecular and cellular changes, the damage is continuing to accumulate. So anything that tries to attack the consequences of that damage is inevitably going to become progressively less effective as there is more and more damage. So it's completely hopeless. A century ago, a few people started to realize that, and they said, well, instead of that, let us try to slow down the creation of damage. Let us try to get inspiration from the living world, in which there are some species that live a very, very long time. Maybe we can figure out how they do that, and we can get humans to live longer as a result of effectively getting the body to run more cleanly, to create damage more slowly. But that hasn't worked either. And the reason that has not worked is because the body's creation of damage is just too intrinsic. It is too inextricably intertwined with the things that we need the body to do to keep us alive. We hadn't had no success at all, really, in making the body run more cleanly. And for that reason, everyone basically gave up. Maybe 50 years ago, people were not even thinking about doing anything about aging. But then in 2000, I realized that there is a third way to separate our metabolism from the pathologies of late life, and that is to do preventative maintenance. To leave both of the two processes that combine to make up aging, to leave them both alone, but to separate the processes from each other by periodically removing the various types of damage that the body is creating.
Are you referring to the 7 categories of damages, I guess?
I certainly am, yes. The great thing about this preventative maintenance approach is that we are effectively sidestepping our ignorance of how the body creates damage, of the processes that generate these changes. But what we are certainly not sidestepping is what the damage itself is. We have to characterize the damage. We have to say what is different in the molecular and cellular composition of the body of a 50-year-old relative to the body of a 20-year-old. Once we can do that, then we know what our targets are for repairing the damage. The thing is, we already knew a lot by 25 years ago about what changes occur. What are the molecular and cellular differences? So that's great. Now, of course, some of those differences may be harmless or even adaptive. They may not be things that we want or need to fix. But that's okay. We can find that out just by trial and error. We can fix things and see what happens. The question then is, how can we develop methods to do this repair? And as you say, 25 years ago, I developed a classification of these many types of damage into a manageable number of categories, just 7 categories. We can describe a generic intervention, a way in which we can repair each of the types of damage in a given category in more or less the same way. So, for example, one of the categories is the loss of cells, where cells die and they are not automatically replaced by the division of other cells. So, of course, the number of cells goes down. Eventually, there are not enough of that type of cell to do the job that's necessary. What do you do about that? The generic answer is stem cell therapy. You put cells into the body that know what to do, to divide and to replace the cells that the body is not replacing on its own.
And does that work?
Oh, yes. So there are various parts of the body in which cells are lost, and they contribute to, or maybe they are the main contributor to a particular type of aging. So, for example, Parkinson's disease is caused by the loss of a particular type of cell in the brain. The decline in the immune system, which happens late in life, is largely caused by the loss of cells in a particular place the organ called the thymus, things like that. And even heart failure, there are cells in the heart called pacemaker cells, which are responsible for maintaining the heartbeat, and we lose those. So yes, the question is, does stem cell therapy work? The case that is perhaps easiest to describe at this point is Parkinson's disease. In that case, people have tried it. And when they first tried it, it only occasionally worked. That was because this was 30 years ago, and we didn't know very much back then about how to make sure we were using the right kind of stem cell. But it still worked occasionally because they got lucky sometimes. And when it did work, it worked spectacularly well. People who had fairly advanced Parkinson's disease, they completely eliminated all the symptoms for at least 10 years just with one injection of stem cells. So now, of course, we know a lot about how to manipulate stem cells, how to use the right kind of stem cells. So everyone has come back to this idea. And there are now, I think, 5 clinical trials going on right now, and everyone's very optimistic.
Dr. De Grey, I do have a question because I did a podcast with Sandra Kaufman, and she also is using the 7 tenet approach. What's different? I mean, from the why there is this 12 hallmarks of aging then? It's just
Right.
like very confusing.
So you mentioned in your introduction that when I first started talking about this kind of divide and conquer approach, there was a lot of debate, and some of it was quite acrimonious, actually. A lot of people said that this whole approach was not scientific. They didn't really understand anything I was saying. But after about 10 years of, repeating myself and explaining myself and so on, I pretty much won the argument. And that was first really, the end of that whole period was really marked by the publication of this paper called The Hallmarks of Aging in 2013. There were 5 very distinguished colleagues who got together and wrote something which was basically a restatement of what I had said more than 10 years earlier. Its time had come, so to speak. So that paper has become by far the most highly cited paper in the whole of the biology of aging this century. And that's great. The argument is over. But the thing about the Hallmarks paper was that it kind of missed the point. It described the types of damage. It didn't do it quite completely, actually. It left a few things out, but it was not bad. But in terms of how to deal with the damage, it talked about some of the same things that I talk about, but it also talked about other things that were just fashionable, really. Some people have said rather unkindly that my paper described, was a classification of aging, and the Hallmarks paper was a classification of the literature on aging, which is not completely fair, but not far off. Anyway, but the point is, because of that, the Hallmarks, as described in 2013, have had to be continuously updated. There are sometimes, 12 or 14 or whatever. It's kind of, because of this, like missing the point. Whereas my classification has very much stood the test of time.
I see. Okay. It's just like, there's so much information out there, and at some point people get confused because, just like, very famous popular names are throwing some ideas out, and they are assuming that they're going to live until they're 150 years old. And the first person who told me that that's not going to happen was Liz Parrish, actually. She says, like, if technology doesn't change, no one is going to live until 150 years old. I know that one of the biggest obstacles that researchers like you are facing is the funding. And you're really criticizing people who are kind of using their money just for themselves to begin with. And then secondly, on things that it's not going to really make a difference.
Yeah, this is true. Certainly we absolutely will not see anyone living to 150 or even 130 unless there are big advances in the kinds of medicines that we can give people. It is critical that we should develop these medicines. In fact, without these medicines, we're probably not going to make more than a few years of difference to how long people live relative to, where they are right now, because we've done all the easy stuff. People in the industrialized world, hardly anyone dies in infancy anymore because we just have brought those infectious diseases under control. It would be nice if wealthy people would, do the right thing. And it's got better. When I started, essentially nobody was putting money into this area. And then gradually that changed. Unfortunately, there's a second problem, which is that when people finally decide, yes, they're going to put serious money into this space, they don't take good advice about how to do it. So, for example, in, I think, 2013, the people who founded Google, Larry Page and Sergey Brin, who had known me for at least 10 years at that point, they decided to create this company called Calico. And it has been a complete waste of billions of dollars because they just, structured it according to, what they personally felt was a good way to structure it. And it was completely wrong. If they actually, taken proper advice from me or someone else, then they could have done a lot of good. Things are improving, though. So more recently, Jeff Bezos put $3 billion into this new company called Altos Labs. Altos is also, the jury is out on Altos, I would say. But they've done some things right. They've hired a lot of the top scientists in the field, and scientists with different ways of thinking. So there is a good possibility that there will be a diversity of approaches going on. However, one thing that is unfortunate is that, just like Calico, they are a company rather than a non-profit, and the result is they hardly talk at all about what they're doing, which is a great shame. We are getting far too little information about what progress is being made. The really best example right now is a company called Retro Biosciences, which was bankrolled to a smaller amount, but still quite a lot, 180 million, by Sam Altman, the guy who created Y Combinator and OpenAI. And that company is being run correctly, largely because it's being run by somebody who actually talks to everybody else and who knows the science well. So, things are improving. But yes, it's painful how difficult it is to get wealthy people, first of all, to understand that this is an important problem to work on. Second of all, to actually write big checks, even though they became wealthy by being careful with their money. And thirdly, to write big checks in the right way and to actually make a difference with that money.
You just mentioned that without these medications, it would be even difficult to extend life for a couple of years. What do you mean by these medications? What are they? Are there any specific things that are already out there or some things that you guys are working on?
I mean the damage repair approaches that I've been talking about all these years. So I've mentioned stem cell therapy for Parkinson's disease. Even that is still only in clinical trials. It will still be probably a couple more years before it can be prescribed. Various other stem cell therapies are in the same kind of situation. Some of them are available offshore, for medical tourism. Some of them are available in the US, but only in certain places. Many of them are not covered by insurance, so it's restricted availability. Other types of damage repair are typically even less far along. So, for example, one of my categories is what are called senescent cells, cells that in a kind of toxic state, and the immune system tries to get rid of them, but it does not completely get rid of them. And so we need drugs that get rid of them, and those drugs now exist, and some of them are in clinical trials, but again, they're not yet available to be prescribed. So we're getting there pretty quickly.
So question, before we move forward, because I know Senolytics, I mean, it's like one of the very popular word in the supplement world now. Like, this is a Senolytic, use this every 2 weeks, whatever. Any of these works, you think?
The Senolytics that are already available are typically natural compounds, like Fisetin. Yeah. And they are not very good. There is good evidence that they have some effect on senescent cells, but I have not yet seen any data anyway showing that the effect is substantial. I think we need better Senolytics. Now, the thing is, we do have better Senolytics in the laboratory that have been used on mice, and they definitely kill off a lot of senescent cells. But just like the stem cells and so on, those Senolytics will not be available to be prescribed for maybe another 5 years.
You just recently completed a 1,000 mice experiment. It's like a lot of mice. I think you're the first person who did such a big experiment, correct? If I'm not mistaken. It's very difficult to get that many mice. I heard from my researcher friends.
Yeah, it's pretty tricky. We got them from a place called Jackson Labs, which is in the US. And yeah, there's only one strain of mice that you can get that many mice if you want to start late in life, which is what we did. These mice live about 2.5 years. We started the experiment when they were already 1.5 years old. So yes, you're quite right, 1,000 mice. But actually, you can get a lot of those particular type of mice. And those are the particular type that are used for nearly all lifespan experiments. So the next experiment we want to do will actually be 2,000 mice.
So I think that, based on what I listened from your lectures, I was trying to get ready for this podcast, you're kind of coming to the conclusion that one intervention would not be enough. You kind of need to do this group of intervention, like maybe target all these 7 categories that you're trying to target.
Yeah, so it's a bit better than that, but more or less you're right. The thing about damage repair is that it is inherently a divide and conquer approach, because different medicines will be repairing different types of damage, and the body, of course, is a very, very complicated machine. It does itself a lot of different types of damage. But the good news is that the processes that create this damage are somewhat interconnected. We don't understand those processes very well in many cases. And as I mentioned earlier, the great thing about the maintenance approach is that we don't really need to understand the processes. But what we do see is that if you repair just one type of damage, then you can often see benefits that do not seem to relate to that type of damage, as if there is kind of a knock-on effect where the creation of other types of damage slows down as a result of, if you like, taking pressure off the body by removing one type of damage. The first time that this became really conspicuous was when the first senolytics were developed, or to be more precise, the first genetic model of senolytics, where they made special mice that had a particular gene so that you could just kill off all the senescent cells with a drug that is not actually a senolytic. The benefits to the health of these mice were much more widespread than anyone had expected. So that's one good news. It means that even though there are 7 categories of damage, and within each category there are various different types, nevertheless, just a few types of damage repair may be enough to give a big effect in terms of lifespan, at least in mice. Yeah. So when we did our first experiment, we had just 3 types of damage repair, plus 1 calorie restriction mimetic called rapamycin. In the next experiment, we want to have 8 different types of damage repair, and we are optimistic that that will be enough to get a really big increase in lifespan.
Sandra Kaufman says a joke about actually senolytics and the senescent cells. She goes like, when you get old, very old, I mean, not like maybe 50, 60, but in your 80s, and if you take senolytics, then you will be just a pile of a dust on the floor because you only have zombie cells, senescent cells.
Luckily, that's not true. Even in old age, way less than 1% of our cells are senescent. That's why we can do this. The reason why such a small proportion of cells are still doing a lot of damage is because they are actively toxic. They're not just inactive. They are secreting things that make the rest of the body unhappy. So that's the key advance. 30 years ago, nobody had thought of that. Everyone was just thinking, well, senescent cells don't matter very much because we don't have very many of them. But then a fantastic researcher who died a couple of years ago named Judy Campisi, great friend of mine, realized that senescent cells might be actively toxic and that this might be what was really going on. And she was absolutely right.
So what are the interventions today that we are doing or it's doable that it will at least help a little not to have these 7 damages or have less of them?
First of all, yes, you're quite right to emphasize that what we can do today can only give a small amount of benefit. But let me explain that a little better, because most people will look at headlines and think that they can get a lot of benefit. That's making kind of the wrong comparison. We do know that it's easy to shorten your life, to accelerate the accumulation of damage. Obviously, smoking or getting seriously overweight or, having a very, unnatural diet, with processed food. But that's not really the right comparison because we knew all that. So the correct comparison to be making is to say, well, okay, let's say that the baseline is simply living the way your mother told you to, right? So in other words, not doing anything special, but just, being well behaved. Then we have to ask, relative to that, how much improvement can we make? And the answer is very little, maybe a year or 2 if we're lucky. But I want to emphasize that, that's better than nothing. So it's definitely a good thing to do all this. However, the key other thing I have to emphasize is that people are so different from each other. So there is no one thing that will benefit everybody. In fact, some things may benefit some people and actually do harm to other people. So the critical thing is measurement. the biggest thing that you can do is to know your body well. And some of that comes down to just common sense, paying attention to your bodies, doing things that don't make you feel sick. But a lot of it is, measurements by medicine. So taking samples of your blood and seeing whether certain things that you don't want are high, like, glucose or insulin or peroxides. Then also, of course, your genetics. It's possible to sequence one's genome for less than $1,000 now, so most people can do that. And you find things out. So, for example, I just take one supplement right now. It's called methylcobalamin. It's a type of vitamin B12. And the reason I take it is because of my genome. I have a variant of a particular gene called MTHFR, which is responsible for giving me an elevated level of homocysteine in my blood. I'd known for 20 years that I had elevated homocysteine, but it didn't seem to be doing me any harm, so I didn't do anything about it. But now I know the reason and how to fix it because of my genome.
So you're not taking anything else?
That's right. I'm one of those repulsively lucky people. I get measured a lot. I have been measured a lot for 20-odd years. Not just my blood, lots of cognitive tests and, tests of my strength and my endurance and VO2 max, lots of things. And I always come out at least a decade younger than I really am. So I'm just, and I can eat and drink basically what I like and nothing happens and I don't even need to do any exercise to speak of. So I'm just one of those lucky people.
Or maybe you think that, doing all these things that maybe we are doing or we're influenced to do is not going to make much of any difference. So you just prefer to live your life.
No, that's not the case. I certainly would not recommend that other people should do nothing just because I do nothing. But however, if you're lucky like me and you're doing really well for your age, then the sensible thing to do is to be conservative. If it ain't broke, don't fix it, as they say, right?
I was just trying to joke, but how do you feel about these new technologies that are trying to help people, partial gene therapies? I did an interview with Patrick Sewell and I learned a lot from him. I learned a lot from Liz Parrish. So do you think that they will have any influence on what you're trying to do?
I'm quite sure that they will. I'm quite sure that when we finally develop a comprehensive panel of damage repair methods that are, that work on people, that some of those methods will indeed be gene therapy of one sort or another. The thing about gene therapy is that it's still, got a long way to go just in terms of the delivery of the genes, even setting aside which genes we're going to deliver. And so if you look at the range of clinical trials that are going on now, you find that nearly all, well, not all, but at least 70% of the things that have been approved and that are close to being approved for diseases in the eye. The reason for that is because the eye basically doesn't have an immune system, and the immune system gets angry when you do gene therapy. Not because of the genes that you're delivering, but because of the way you deliver them, which is by using an engineered virus of one kind or another. The immune system notices these things and gets angry. So in the eye, that doesn't happen. And the result is you can do quite a few things with gene therapy. There's one thing that was an idea I had many years ago, which is being used now against macular degeneration. The idea was basically macular degeneration is caused by one particular type of damage, which is the accumulation of an indigestible compound in the back of the eye in the cells called the retinal pigmented epithelial cells. And, the reason it accumulates is because we just don't have machinery to break it down naturally. It accumulates really slowly, which is why we don't get macular degeneration until late in life. But we do eventually. So what do we do about that? I realized that we might be able to find bacteria in the soil that are able to break down this compound. It turns out that you can find bacteria that can break down remarkable things like, TNT or dioxins or whatever. And of course, they do not break these things down in order to live longer. They break these things down in order to extract energy from them, to live off them. But that's okay. It doesn't matter why they do it, the fact that they do it. So then when you find bacteria that can do this, the idea is not to inject those bacteria into the eye. That would be a very bad idea. But what you can do is to identify which genes they have that make the enzymes that allow them to break the thing down. And we did this. It was a long project to get it to really work, but now it's been taken forward by a company that was a spin-out from one of my previous organizations, and it's about to be sold to Big Pharma, so it's going quite well.
What are your thoughts about rapamycin?
Rapamycin is a very interesting compound, but it's not all that interesting for human beings. The reason why is because it's what's called a calorie restriction mimetic. In other words, it's a drug that tricks the cell into thinking that it's not getting enough energy when actually it is. Essentially, it tricks the body into thinking it's in a famine. Now, the thing about famine is that it's something that really happens in the real world, and therefore evolution has figured out how to optimize the way the body works so as to maximize the chance of passing on genes from one generation to the next, even when famine happens. If you think about it, that comes down to a prioritization of growth versus maintenance. So if you're in a normal environment with lots of food, then the main challenge, the main barrier to passing on your genes is being eaten by some other organism. What you do is you grow as fast as you can, and you reach sexual maturity so that you can have offspring before you get eaten. That's the logical thing to do. But in a famine, you don't really want to do that, because if you have offspring during the famine, they will starve to death before they have their own offspring. So it won't be effective. So the sensible thing to do in a famine is to hunker down and to grow more slowly and to just stay out of trouble and give yourself some chance anyway of being alive when the famine is over. And all organisms do this. There are very general mechanisms that species have for making this happen. And it turns out that there are drugs, rapamycin is probably the best one, that effectively make the cell think that there's a famine, even though there isn't. And, of course, that means that the cell does the same things. It turns on and off the same genes that it would in an actual famine, and the result is the same. The organisms live a bit longer. But here's the catch. The problem is that long famines less frequent in the real world than short famines. And that means that the evolutionary pressure, the selective pressure to develop ways to respond to long famines is just weaker. So effectively what that means is that long-lived species like humans get less of a benefit from calorie restriction, from actually eating less, than short-lived organisms do, like mice. And similarly, humans get less benefit from a calorie restriction mimetic, like rapamycin.
So you don't believe that we should use it? I mean, it's not going to make much of any difference.
It's like the other things that we can already do. It may give some benefit, but not very much. So I'm not against it at all, but I want everyone to understand that it's not the fountain of youth.
I think you're using in your research studies, correct, with the mice?
We did use it as one of our 4 interventions in the study we just did. But we knew that everything I just told you. So effectively it was what scientists call a positive control. We wanted to see that we were doing the lifespan experiment correctly, and therefore we wanted to see that rapamycin worked to the same extent that it normally works in mice in other previously published studies. But the real point of our experiment was the other 3 interventions, which were genuine damage repair.
You know, of course, everybody's in their mind, there's this thing. So what are these guys are trying to achieve? Like, okay, I understand we're trying not to make people old, but what is the end goal? Make everybody live forever?
Yeah, right. So everyone says that. But really, no. The end goal is simply to make everyone stay healthy forever. You know, I don't work on longevity. I work on health. Longevity is a side effect of health. Now, I believe that it's a side effect that we should celebrate. And a lot of the more politically correct people in the research field are bad at that. They often speak about extension of life as something that we shouldn't talk about, something that, yes, it is the side effect of staying healthy, but we should kind of apologize for that rather than celebrate it. I think that's really damaging. But yeah, it's a side effect. We work on health. And so nobody wants to get sick, however long ago they were born. So as far as I'm concerned, I'm just a humanitarian.
Based on your researches, even though you do it on mice, is there like a limit on how much the cells can divide and how much can someone live until?
No. So this was a kind of misstep, a kind of mistaken direction that the field took in the 1960s, when people discovered that there was only so many times that a cell could divide before it just stops. The thing is that the type of cell that was used for this experiment is something called a dermal fibroblast. Now, these are cells that are responsible for wound healing. If you have a scratch or whatever on your skin, then these cells divide very rapidly to close up the wound and prevent an infection from getting in or anything like that. But that's all. Normally, when there's no wound, they don't divide. They just sit there and do almost nothing, right? The fact that they can divide so well when they are stimulated to do so, that's the reason why they are used for these kinds of experiments, because it's easy to grow them in a petri dish, or whatever, in the laboratory. But when you make these things divide forever and ever, then that's not a physiologically relevant thing, right? It's as if you're making the cells think that they are in this infinitely large wound that they're unable to close, right? It was really, it's completely irrelevant to the body. Now, there are other types of cell in the body which do divide regularly, quite frequently. In particular, the stem cells in the lining of the gut, the stem cells in the bone marrow. But these cells have a trick that means that they do not need to worry about this process called replicative senescence. They express an enzyme called telomerase, just a very small amount of it, but that's enough to stop this process from happening so that those cells can divide indefinitely. There's just one example of a cell that may be in a state where it gets this problem, and these are called memory cells of the immune system. If you have an infection, then the immune system obviously gets rid of the infection, but it also maintains, after the infection's gone away, it maintains a small population of cells called memory cells, which allow the immune system to respond much more quickly if you get the same infection again. All right? Now, there are some infections called herpes viruses, cytomegalovirus is one of them, which actually are a bit unusual in that when the immune system attacks them, it does not get rid of them completely. You have some residual virus that persists in the body in a kind of latent, inactive state. And then later on, that same virus can reactivate. So that's like getting an infection for the second time. But it happens much more often than for an actual infection that the immune system really does get rid of completely. So the memory cells that are specific for these persistent viruses do get into this state called replicative senescence that you were talking about. But that seems to be the only example, at least it's the only one we know about.
So it's just like there's an indefinite division that they can go through. At least that's great because, when I was doing a podcast with Bill Andrews, his theory was like, do not work out hard, don't do any facial treatments, don't whatever to make your cells or your telomeres had the need to divide or lose some of their capacity, let's say.
Yeah, so Bill thinks that if we have more telomerase, this enzyme that I mentioned that allows the stem cells in the gut or in the bone marrow to divide indefinitely, if we have more of it, then that will be good for the rest of our cells. And Liz Parrish, who works closely with Bill, she obviously has done gene therapy for telomerase. I'm not so sure. I mean, I'm pretty sure that it's not true. However, it's not completely certain because people have done that kind of experiment in mice, and indeed we did it. It was one of the things that we did in our study that we just completed. And it does extend lifespan of mice. It looks as though the reason it works in mice is because mice are really, really, really bad at DNA maintenance, at protecting their DNA normally in life. So the telomeres, the ends of the chromosomes, get shorter at a much more rapid rate. But that's not because of cell division. It's because of other types of damage that happen during the life of the cell. So when we see senescent cells we certainly see in humans as well as in mice, those cells are a bit like cells that have got into this state I was talking about, where they've divided too often. But they got that way by a different mechanism, by DNA damage of some kind.
I keep listening to you because I'm speaking finally with the person that is really, really working hard to make that longevity escape velocity happens, and that's the name of your foundation. Actually, I had to translate it and understand what it really means, and my producer finally explained it to me, gave an example with the rockets that going to the sky and how they went through this lining of the atmosphere, I guess. You're working on health, you say, and your goal is not like creating this longevity for forever, but when what you're working and what others are working gonna start working, then did you ever think that we're never gonna die? And I mean, how the world would be? Or you're gonna just think about that when the time comes?
Of course, I have thought about it quite a lot. And I'm not the only person who has thought about it, not least because every single time I do an interview, people ask about it.
Of course.
So, yes, of course, the world will be very different when there are no sick people anymore. At the moment, a huge amount of how we have constructed society revolves around the fact that people get sick when they get old, and that will not be true anymore. Things will be very different. We will have a very different kind of generation gap. You know, people will relate better to their grandchildren when they are able to keep up with their grandchildren on the dance floor. People, the way that people spend money at the moment on big things like, health insurance or life insurance or pension plans, these things are all based on how long people expect to live, right? Sure. And at the moment, people expect to live only a few years longer than their parents did. But very soon, people will start expecting to live essentially indefinitely. And that will very much change what kind of ways they want to run their life. People may very well have children at a much later age because they can. Whenever a country goes through this thing called the demographic transition, when women have enough education and emancipation and so on, so that they can do a lot with their lives, then there's a huge, very sharp reduction in how many children the average woman has. Mm-hmm. But at the same time, there is always an increase in the age at which women have those children. Mm-hmm. So, on average. So, of course, the reason for this is simply that women want to do other things with their life before they do this terribly time-consuming thing called having kids, right? When we eliminate menopause, people will be able to have kids safely at any age. Then they may very well delay having their kids by another decade or another decade or another decade. Of course, you may have some people in the audience who are looking forward to menopause and to no longer having periods.
Their period, yeah.
So I should point out that the technology here will be able to turn it on and off. It's not something that would necessarily be permanent.
I have 2 or 3 questions connected to each other, so I'm going to list them one after the other. One is that I know that you have some prediction, maybe like 2 decades or even less, to be able to resolve this issue. But more so, how are you going to translate what you're working on mice into human? Because obviously we're not these. And when everything is resolved and now you have the interventions, not one, but multiple interventions to help someone, do you think there will be a certain age that would work, like before this age or after that age? Or is it going to be helping someone to never get these damages? Let's say that you're 20 years old or you're whatever, what the governments would allow, and they will start receiving these interventions. Therefore, they're never going to create these malfunctioning cells and stuff.
First of all, let me answer the second question about the age at which people would receive these treatments. These treatments are preventative in the sense that they are supposed to be given to people who are not yet sick. But they are also treatments in the sense that we will be reverting somebody to a younger biological age, so effectively rejuvenating people. So what that means is that the ideal age at which people should start receiving these treatments is maybe 50, though it can vary from one person to another, given people's natural rate of aging. But then after that, they will receive the treatments every so periodically, because in the same way that you have to do preventative maintenance continuously, every year or whatever on a car, similarly for the body. Yes, people will never actually get sick because they will never have enough damage in their body to make them sick. So with regard to the first question about translating these things from mice to humans, this is very important to understand. Everyone knows that most things that work in mice against particular diseases do not work in humans. And that's why we need to do clinical trials on humans before we make something available to the public. First of all, we still do mouse experiments anyway, because if something works in mice, then at least it has a chance of working in humans, whereas if it doesn't even work in mice, then you can forget it, really. So that's important. But what's more important here is, let's call it the rhetorical aspect. At the moment, the progress that we are making in extending mouse lifespan is pretty much zero. If you do the experiments that I've been describing, where you take mice that would normally live for 2.5 years and you start treating them when they're 1.5 years old, then the amount that we can so far extend their life is about 4 months. Okay? Mm-hmm. If you ask that same question for the situation 50 years ago, you say, okay, you take mice, live 2.5 years, you start treating them when they're 1.5 years old, how much can you extend their life? The answer was 4 months. We have made no progress in half a century. So, it's pretty reasonable for people who could write big checks, like the government, for example, to say, well, there's no progress, you don't know what to do, therefore there's no money. But if we do make progress in mice, and I believe that we can by doing this, multiple approach, this combination approach, if we get, let's say, 12 months of increase in the same experiment, so 3 times the effect size that we can currently get, then everybody, all the experts are going to know that we're in a different world, and they will say so. And that will change public attitudes, and that will change public policy. So essentially, my slogan these days is I say, I want to make aging the new COVID. I want to have society think about aging the same way that it thought about COVID 5 years ago. What happened 5 years ago was really important. We suddenly had this new problem, and society believed that we could solve it if we tried. And society wanted to solve it as quickly as possible. Vaccines were developed and distributed globally in less than 1 year. Now, what you have to know is that before then, the fastest that any vaccine had been developed and distributed was more than 10 years. So we did things 10 times faster. How did we do that? Simple. We tore up the rules. Governments around the world just completely ignored the regulations that they themselves had written in order to get the stuff done as quickly as possible. And they did so because the public wanted them to, and they wanted to get re-elected. That was all, right? What was the difference? I mean, the fact is, in order to do this, a lot of corners needed to be cut. And I think we can now say that some people suffered as a result. Some people, have long COVID, or they have situations that are probably caused by the vaccines. But that's fine. That's a good thing, because the number of people that have suffered is a teeny tiny fraction of the number of lives that were saved by getting that vaccine out in 1 year instead of 10 years. That's the attitude that we need to have when we look at aging properly. And I believe that by getting sufficiently dramatic results in the laboratory, we have a good chance of being able to make that happen.
What do you think is holding you back besides the finances? Are there any other ideologies and stuff out there that is not really helping you guys to progress your researches?
Really, no. Everyone wants this to happen. All of the scientific community is very much behind these kinds of experiments. They really want them to happen. The wider world, is very interested in the work that we're doing. So no, I think it's really just the money.
I have a very active social media, and I sometimes share like my interventions over there. I keep receiving these messages like, why are you so much trying not to die? Or start hanging out with much younger people because, we're all going to go and you're going to be staying here with them. Like, there's all these obnoxious sometimes critical, sometimes, sarcastic approaches. So like you said, it has to be something for the whole humanity to look at it as a scarcity, not like something like, oh, I want to live longer.
Right. The whole idea of focusing on the longevity increase is it's a psychological trick. It's like it allows people to put aging out of their minds by essentially saying, oh, people who want these treatments are being selfish or whatever, or in many other ways. People will say, doesn't death give meaning to life? Or they'll say, won't dictators live forever? Or they'll say, how will we pay the pensions? All of these arguments are completely infantile. They're completely ridiculous. But people still stick to them. It doesn't matter how often you tell people why the arguments make no sense. And the reason they stick to them is because they don't want to get their hopes up. They're terrified of becoming emotionally invested in this and believing that these treatments are going to come along in time for them or for their parents or whatever. And then progress is slower than they were hoping, and so they get disappointed. They just, they can't stand that possibility, so they put it out of their minds by making up these fairy stories.
I think that, one thing that make people realize that the researches today shows that younger generations now are not going to live as long as we're going to be living with all the insults that we're getting in this lifetime. So maybe that will make them be more mindful of to fight with what we're encountering, because they're going to be more Wi-Fi, they're going to be more flight, more pesticide, more of anything and everything that is going to be harming and damaging our biology.
Yeah, I think that argument is probably not really correct. There are lots of things that technology has given us that have, both positive and negative consequences. But in general, even though the progress is not uniform, it still happens. A great example would be the immune system. So, of course, hardly anybody dies of infections early in life in the Western world anymore, whereas 200 years ago, lots of people did. That has had a consequence for the strength of the immune system. People now have weaker immune systems than they did 200 years ago. So if modern medicine suddenly vanished today, we would be in real trouble. But modern medicine isn't going to vanish, so that's okay.
So you're saying that we're getting actually stronger by fighting with what we're facing day in and day out.
That's right. Technology is making life better.
Of course. No, of course. No, I'm agreeing with it. What I was trying to say is that, there are more negative things affecting our biology. That's what I was trying to say. Well, that was a great talk. I learned a lot. One last question. When do you think, really realistically, this thing would be resolved?
Of course, this is pioneering technology, so I can only give a probabilistic answer to that question. I think that we have a 50% chance of getting to longevity escape velocity, which is basically getting 20 years of additional healthy life for people who are already in middle age when we start treating them. I think we can probably do that within the next 12 to 15 years. So by the end of the 2030s. That depends on making progress in mice in the next 5 years so that we can make aging the new COVID. I think once that has happened, once we make enough progress so that society really starts trying to bring aging under medical control, then it will take less than 10 years from that time. But that's, as I say, only with 50% probability because this is scientific technology.
Yeah, you're absolutely right. Well, I think that this last sentence really explained what you're trying to achieve. Not like, because the word of longevity, like, living forever, living until whatever, it's really, maybe that's the scary and different part of to humanity, to live that long. What you're actually saying is like, we're trying to solve the illnesses so that you will have a healthy life, whatever you live 20, and if you don't have kidney disease or diabetes or cancer, whatever, so you can definitely live another 20 years without these diseases. So that's the goal. Dr. De Grey, thank you very much for your time. I feel very special actually in Turkey that I'm the first person who had the chance to interview you, and you're amazing, and keep doing the hard work because you're the person who's working on this.
Well, thank you very much for having me on the show and for being so interested in this work.